Okay, this video is a follow-up to our notes on magnetic fields and curl right-hand rule. I wanted to go over the practice problem in case you didn't get that answer. So this problem says, the diagram is showing three parallel wires, P, Q, and R, and they each have the same current I. What direction is the resultant force on Q due to wire P and wire R? So our focus is really what is going to happen to Q. Is Q going to feel a force to the right, the left, or no force at all? Maybe up, down, into the page. So we're going to try to figure out what the force for wire Q is going to be. So the first thing I'm going to do is focus on the interaction between P and Q. I'm noticing that P is downwards, and I know that any current carrying wire is going to create a magnetic field. So I'm going to point my thumb downwards and use the curl right-hand rule, curling my fingers around P to find out that this magnetic field that's created from P is into the page on the left and out of the page on the right. I'm also going to do that for wire Q, noticing that Q is also downwards current. So the magnetic field created by that current, pointing my thumb down, curling my fingers around, I have a magnetic field that's going into the page on the left and out of the page on the right. Now I'm going to focus on the region between P and Q, noticing that we have opposite magnetic fields here. We know that opposite magnetic fields are going to create an attractive force. So that means that wire P is going to be pulled to the right and wire Q is going to be pulled to the left. They're going to attract towards each other. Remember, our focus is on wire Q, so we don't really care that P is being pulled to the right for this problem. But we also need to remember that, yes, wire Q is feeling this force attracting it over to P, but it's also going to interact with the magnetic field created by wire R. Noticing that wire R has a current that's upwards. Every current carrying wire is going to create a magnetic field. I'll use my curl right-hand rule to find the direction. So I'll put my thumb upwards, curl my fingers around. That curl is going into the page on the right and out of the page on the left. Going to focus on this region where the magnetic fields are overlapping, where they're interacting with each other, noticing that these are like magnetic fields. We know that like magnetic fields are going to repel each other. That means that wire R is going to go to the right and wire Q is going to go to the left. Again though, this problem is asking us the resultant force on wire Q. So I'm going to zoom in just to wire Q in the middle. And I'm noticing that wire Q has a force to the left and another force to the left. One attracting it over to P and one repelling it from R. Those forces in magnitude would add together, but this question is only asking for the direction, so we know the resultant force must be to the left. One question that you might have is, how would this problem change if you didn't have all of the same currents in the problem, if all the currents weren't just I? Well, in this particular problem, what that would mean is that our two arrows, one would simply be longer than the other, but the resultant force would still be leftwards. But if we had a different configuration with different currents, where maybe you had like a leftward force and a rightward force acting on a wire, and let's say because the currents weren't exactly the same, those forces were unbalanced, you would need more information in order to calculate the magnitudes and actually find the magnitude of each of those forces in order to see which one's bigger, smaller, what is the net or resultant force. Fortunately, this problem didn't ask for it, and I haven't seen many IB problems that do.